Hello everyone, this is Wei. I will introduce our proposed framework, context-aware pruning for semantic segmentation. Semantic segmentation is a challenging computer vision task that aims to label each pixels in the image with a semantic class. The figure on the right shows the visualization on Cityscape's dataset, which is a large-scale urban dataset. Each color represents a single semantic class. It has many applications like autonomous driving vehicle and robot navigation. Although the state-of-the-art models are mostly well-performed, there are several existing problems. Firstly, they require a large storage size in general. For Cityscapes, PSP.NET requires over 70 megabytes to store the parameters, and during runtime, it needs more memory for the intermediate outputs. On the other hand, using a small model like eNet may sacrifice the accuracy aggressively. Second, their runtime speed are quite slow on even high-performed GPUs, where many of them are far from the real-time speed bar. These two problems hinder the deployment of these deep neural networks on the embedded systems, like the wearable and mobile devices, which have limited computational resources and strict requirements. To solve the problems, one research direction became popular recently, that is network pruning. It aims to remove the model redundancy without losing too much the original performance and achieve a faster inference. The demo is an example for pruning in neurons level for a two-layer neural network. However, there are limitations of the existing pruning methods. That is, they focus only on the image-level classification and they cannot perform well on the more challenging task, semantic segmentation, also known as the pixel-level classification. For the preliminary, we first bring up the concept of contextual information. Intuitively, it means how the surrounding objects are associated with the object of interest. For example, if the object is a boat, its contextual information include all the surroundings like trees, water and sky. And from the feature map's perspective, it is about how the channels each layer are associated with each other. Contextual information is important, since it can help us to predict the object semantics more confidently. For an object on the water and near the shore and trees, we would believe it is more likely a boat. In addition, among all surroundings, water provides more crucial information for the prediction than others. Since the contextual information is so important, can we leverage it to guide the pruning for deep neural networks? It has been achieved by our proposed framework, where we tend to preserve channels that provide such important contextual information, like water, and to discard the ones that offer less important context, like sky and grass. Our framework includes 3 steps. First, to learn the contextual information through the association of channels. Second, to determine the channel's importance based on the contextual information. Third, to remove the non-informative channels and obtain the compact models. For the first step, given an input image, the activations on different channels association provide different useful features that serve as the contextual information each layer. In the feature maps with 64 channels, the association of channel 1, 62 and 63 may provide the context of water, channel 1 and 2 may provide the context of trees. To quantify these association on high-level feature maps, we propose the context-aware guiding module, which first computes the channel affinity matrix A, and second, the context guiding vector beta. The former one quantifies the interdependency of channels and the latter one encodes how much contextual information each channel contribute for the prediction. The second step is to determine the channel's importance based on the computed contextual information. Concretely, we leverage the context guiding vector, beta, and formulate the optimization, context-aware guided sparsification, to induce channel-wise sparsity adaptively, and reveal the redundancies in the cumbersome model. It has 2 goals. The first goal is to solve the segmentation task by minimizing the loss term L theta. The second goal is to sparsify the channel's importance, that is, the channel-wise scaling factors, gamma, in the batch normalization layers, with the penalty terms. The first term is the regular penalty RS, and the second is the contextual penalty term RC. Vector beta provides the penalty guidance. The larger the interdependency level with other channels, the less the penalty strength. The middle diagram illustrates how we determine the informative channels. For the contextual informative channels, their corresponding scaling factors will be relatively large. And for the non-informative channels, their scaling factors will be 0 out. After that, we obtain a sparsified model, on which the redundant channels are now distinguished. The third step is to obtain the efficient network architecture by pruning. Since the important channels are now determined, we can safely remove the redundant channels with 0 out scaling factor. And finally, we fine-tune the compact model for a few epochs to recover the inevitable performance loss due to the parameters removal. The results show our advantage on compressing not only the large models, like PSP.NET, but also the lightweight models, like ICNet. Here are our qualitative visualization results.